Hello everyone, welcome to the channel of Algocamp. So now on this particular channel, we are actually releasing a series on data structures and algorithms where we are going to talk about some of the most important data structures and algorithmic topics which are extremely important for your upcoming software engineering interviews. Apart from that, these are some of the I would say topics that are very helpful in your day-to-day engineering job as well. We have already released a couple of series around searching, right? And we got a really good response on that. And from here, we are going to put really some awesome content around DSA. In most of these lectures, we will try to ensure that we focus on the intuition building aspect of the things, that how you are able to think about something, what are some of the things that people actually neglect but are going to clear some of the really important fundamentals. We are going to see coding implementation, but trust me, my focus is not going to be on the language delivery aspect of the things, that okay, you have to code this in C++ or Java. A lot of problems we have coded in multiple languages. Maybe some of the problems will be in C++, some will be only in JavaScript. I believe if you are somebody who is preparing for an interview, language in 2025 should not be a constraint, because most of the people can actually use ChatGPT to do language conversions. So my motive here is to make sure that you understand the concept in depth. You actually see how exactly somebody might have thought about the problem when they were carving out the problem, what can be some initial thought process, how you can actually drive yourself towards the solution. I believe these are going to be some really important videos that will be really helpful for your upcoming career. So do let us know what is your feedback. We are going to release a lot of more topics. Do let us know what all topics you want to have first, right? And the feedback is going to be important. Also, in case you are actually thinking to level up, you want to learn things with respect to low-level design, high-level design, overall system design for interviews, or you are somebody who wants to do project development in Spring Boot, you want to learn advanced Spring Boot concepts, or let's say advanced Node.js concepts, then we have a lot of courses, live courses running on algocamp.io. So you can check out the website courses.algocamp.io/learn, and there are a lot of courses that are actually listed. A lot of great discounts are actually going on all the courses as well. Do check them out. For each and every single course, we are going to add you to a dedicated Discord community where you can get your doubts resolved as well. All of the courses, we have made sure that we talk about things from the very beginner to the very advanced level that is going to help you level up in your career as a software engineer. So that being said, let's start the video without any further delay. So there are a set of problems called as kth order statistics, or just order statistics, right? Where in the problem you might be asked to find the kth largest element, kth smallest element, and so on and so forth. And to solve the kth order statistics, there are a lot of algorithms involved, right? Sorting is one of those. There is exist a data structure called as heap, right? Multiple approaches that exist for solving the kth order statistics problem. So here is one of the kth order statistic problem. It says that given an unsorted array of length n and a value k, you need to find the kth smallest element. So this is an unsorted array, and if you're given 2, so the second smallest element you can say is technically 2, or technically if you assume that k is in the range 0 to n minus 1, then if k is 2, then the second smallest element is going to be 3, because the smallest element, the zeroth smallest element is 1, first smallest element is 2, second smallest element is 3. So based on how your question is given to you, you will be having variable answers, right? So this is a problem in front of you, and you have to think about the solution to the problem. One direct solution can be to sort the array. Now if you sort the array using merge sort or quick sort, an algorithm like these, then in order of n log n, you will be able to sort the array, right? Once you have sorted the array will look something like this: 1 2 3 8 9 10, and then you can just return the kth index element from the given array. So the solution that goes by a sorting takes order of n log n time. But in order to solve kth order statistics problem, as I said, there are different approaches that exist. There are a few other approaches also that can solve the problem in k log n or n log k and everything. But can we try to solve the problem in order of n? This is something that might be a bit challenging. How can we solve the question in order of n time complexity? So before we start this particular video, I wanted to actually talk about a very small thing. So this video is going to actually help you understand a real system design interview scenario. We are going to try to mimic a 45 to 60 minute kind of like a round where we are going to solve a problem very similar to how you will solve a similar system design problem in this short time frame. Now, of course, when you work as a software engineer in a company, you have relatively larger amount of time and you can do a lot of more deep dives in even very small level features. But in an interview, the temperament is different, the approach is different, and a similar scenario is actually explained in this particular video. So do consume the content based on that. Also, if you want to see more deep dives and want to understand these topics in a much more deeper level concepts, then do check out the link in the description section below for our System Design 2.0 cohort, where we have talked about a lot more concepts in a lot more detail, which will make you definitely a better software engineer. So let's just start the video. So in order to solve the kth order statistics problem, there exists an algorithm which is one of the most efficient ones to solve this, called as the quick select algorithm. This quick select algorithm is actually based on quicksort only, right? Now, if you think about how we used to do quicksort, in quicksort we used to take a random pivot, right? Then we used to apply the partition algorithm. Using the partition algorithm, we were able to segregate all the elements lesser than x to the left of x, all the elements greater than x to the right of x, right? So in order of n time, we were able to do the partition and then recursively go and apply quicksort on the left half and the right half. Now what I'm trying to say here is that how about after choosing the pivot and applying the partition algorithm, let's say after applying the partition, pivot comes here, right? And at some index I, or let's say some index m. Okay. This is the index of the pivot m after the whole partition and everything has been done. So what you're going to do is you're going to check if, let's say, k is less than m, that is the kth smallest element that you wanted to find. If k is less than m, then can I say that I know everything to the left of x is lesser than x, everything to the right of x is greater than or equal to x. If k is less than m, that is the kth smallest element is less than m, then the kth smallest element is definitely going to lie in the left side of x, because technically this m denotes that this pivot element is the mth smallest element, right? Because now there are going to be some elements to the left of it, some elements to the right of it. If the index of the pivot element is m, then technically this is the mth smallest element. If k is less than m, then can I say that everything to the left of x is going to be lesser than x? And if k is less than m, then our kth smallest element is going to just lie on the left side. We are definitely sure that it is never going to lie on the right side. Can I say that? Right. We are damn sure about the fact that it is never going to lie on the right side. It is always going to lie on the left side. Can I say that? Right. So what we will do is we will just discard the right half and apply the quick select algorithm again on the left half. This is what I'm trying to say. So let me repeat. So in quick select algorithm, you apply the strategy of quicksort. What is the strategy? In quicksort, what do we used to do? We used to pick some random pivot element x. Then we used to apply the partition algorithm. Once the partition algorithm has been done, this pivot rearranges itself such that everything to the left of the pivot is less than the pivot. Everything to the right of the pivot is greater than or equal to the pivot, right? Now let's say after the partition algorithm, pivot is present at some index m. If pivot is present at some index m, then this is the mth smallest element, right? Because everything to the left of x is less than x. And if it is at the mth index, there are approximately what? M minus 1 elements to the left of it, or let's say m elements only to the left of it, because from 0 to m minus 1, there are total m elements. There are m elements to the left of it. So if k is less than m, that is, you were expected to find your kth smallest element, which is less than m, then we are sure that the kth smallest element will always lie on the left side. It is never going to lie on the right side. Can I say that? So we can discard the right half or the right part and pick up the left part. And instead, else, if k is greater than or equal to m, then we are damn sure that k is going to lie in the right part, and left part is expected to be discarded. So we'll just discard the left part and I will only pick the right part. So this time, what's the difference between quick select and quick sort? In quick sort, you go on the left and right, both the parts. You always go on the left part and the right part, both the parts. Whereas in quick select, you always go either to the left or to the right. This is something that you actually do in quick select algorithm, right? That's what we are expected to do here. Now, what will be the time complexity of this algorithm? If you go via quick select, what will be the time complexity? Now, if you assume that there are a bunch of good splits that are happening, then initially the size of the array is n. Then after one good split, what you are going to do? In good split, what happens? If you remember the complexity analysis, in good split, you have n by 3 and 2n by 3. You have two halves, right? So what we will be doing is either we'll be going to the left half or we'll be going to the right half. Let's assume we go to the bigger half always. Let's say 2n by 3. Then again, you do a good split and you go to the right part, that is 4n by 9 and so on, right? So if you take n common, this is 1 plus 2 by 3 plus 4 by 9, 8 by 27 and so on. And this is a geometric progression. Sum of this geometric progression, if you take infinite number of terms, this sum of this geometric progression is actually 3. So this comes out as 3n, and 3n is what? Order of n, right? So the time complexity of quick select algorithm is actually order of n. The one we were able to solve in n log n, we have reduced the complexity to order of n. One quick reminder that you have to keep in your mind is that if let's say k is less than m, then on the left side, you will discard the right part and you will go to the left part. On the left part also, you want the kth smallest element. Just think about it. Let's say your pivot was 9. You have 3, 1, minus 1, 2. And 10, 11, 13, sorry. Let's do 10, 20, 11, 13. Okay. Let's say after the partition, 9 comes here, everything to the left of 9 is less than 9, everything to the right of 9 is greater than or equal to 9. Let's say we wanted to find the second smallest element. Now you can see what is the value of m? 0, 1, 2, 3, 4. M is 4. Is 2 less than 4? Yes. So we are sure that our second smallest element is going to lie in the left part. It is never going to lie in the right part. But let's say you wanted to find the seventh smallest element. Now is 7 less than 4? Is 7 less than 4? No. That means the answer is never going to be in the left part. It will always lie in the right part. Can I say that? Now just think about it. Initially L was here, R was here. That is from 0, 1, 2, 3, 4, 5, 6, 7, 8. In this 8 length array, you wanted to find the second smallest. When you reduced yourself to the left half, in this 4 length array also you want the second smallest. But in case of 7, in this 8 length array, you want the 7th smallest. When you reduce yourself to the right part and L comes here, now don't you think that this is a 4 length array? In a 4 length array, you won't be able to find the 7th element, right? You won't be able to find the 7th element in the 4 length array, right? So you need to make some manipulations, because technically whatever element after sorting would have came to the 7th index would have been your answer, right? Would have been your answer. But now these many elements, L is actually present here. These many elements have been discarded. So how many elements you have discarded? You have technically discarded 5 elements. You have discarded 5 elements. So on the right half, you are not going to search for the 7th element. Technically, you are going to search for the k minus 5, that is 7 minus 5, that is the second element. That is in this right region, you will be trying to find the second element, that is 0, 1, 2. This second element you are trying to find, right? So when you are making quick select call, let's say you have the quick select algorithm, right? From L to R on the given array, you want to find the kth smallest element. What you will do? You will get a random pivot. Based on this random pivot, you will do the partition, right? You will do the partition based on this random pivot. Once the partition is done, what you're going to do is we are going to check if m is equals to k, that is the pivot element is the only element that was the kth element you wanted to find, then you will return ARR of m. The algorithm will stop here. Otherwise, you will check if m is less than k, that means you need to go to the left part, right? How do you go to the left part? You will say quick select L comma m minus 1 comma ARR comma k. Else you want to go to the right part. How do you go to the right part? Quick select. Now from m plus 1 to r you are going to go to ARR, and initially whatever was the kth element, now you want to find k minus m plus 1th element, right? So if m was 4, you technically subtracted 5, right? So it's k minus 5. So you can say you want to find k minus m plus 1, that is k minus m minus 1th element, right? This is something that you can implement, right? Just make sure you check the calculation once if I have done it correctly here. But this is the algorithm that you can implement. Just write a base case also, right? That if L becomes greater than R, then you are going to just return, right? Just add some base cases, and after that you will be able to get your answer. Whatever is your answer, just return from here. That's it. So the difference between quick select and quick sort is that in quick sort you used to make the calls to both left part and the right part, whereas in quick select you just make the call to either left or right, right? Makes sense. And considering that you get some good splits, so for example, if you see the probability analysis for the quicksort algorithm, then technically after every third split is a good split, right? If total region is good, bad, bad, then technically every third split is going to be a good split. We can assume that. So if you go by that, then we can say that mostly we are making good splits. Then n, 2n by 3, 4n by 9, like initially the size of the array was n. You discarded the left half, which was of n by 3, and you took the right half, that is 2n by 3. Like you always take the bigger half, right? And you sum them up. This comes as 3n. 3n is order of n because the sum of this GP is actually 3, right? And that's how you can implement quick select algorithm. This quick select is actually a randomized algorithm as well, because we are actually using the essence of randomization inside it.